Good afternoon. So the purpose of this talk is first of all to do some advertisement or réclame, as we say in French and we say in Russian, I think. I want to advertise a DVD film that I finished. Here it is. So this is 2 hours of mathematics. So I will write the website where you can download it. So this DVD contains 9 chapters of mathematics. Each chapter is 13 minutes long. Now, the first chapter is very, very elementary, probably too elementary for you. The last chapter is maybe accessible, maybe for you. And the level is increasing gradually. I hope you can enjoy it. So the language is in French, English, Spanish, and Arabic, and I hope soon there will be a Russian version. For the time being, we have subtitles in 12 languages, including Russian. So what I propose to show you today is an extract from this film, 2 chapters, so 26 minutes I can sit down, and you look at the film. And these 2 chapters concern the so-called Hopf vibration. So this is one of the most difficult parts in the film. Moreover, I have to apologize because I will put it, of course, with Russian subtitles. And I discovered this morning that there are some small mistakes in Russian. So I am not guilty for that. If you want to complain, just complain to Victor, okay? Anyway, so here's the idea. So we spend 26 minutes looking at the film, and after that I plan to make some comments on the Hopf vibration and maybe about algebraic curves. And to finish, if I have enough time, I plan to explain to you not what I would like to prove, but what I'm trying to understand today. I mean, what I'm reading in my room today. Okay, so let's begin by. So this is the. Let me choose the Russian subtitles. So I hope the can you
pour créer l'arabesque. Afin de mieux comprendre la sphère de dimension 3 dans l'espace de dimension.
Je vais vous montrer comment remplir l'espace par des cercles et former ainsi ce que les mathématiciens appellent une fibration. Au fait, je m'appelle Heinz Hopf et je suis l'un des principaux acteurs du développement de la topologie dans la première moitié du XXe siècle. Regardez cette surface torique remplie par des cercles qui semblent enlacés. Je vais vous expliquer cette figure. Les cercles, les sphères et les tores sont parmi les objets les plus simples qu'étudie le topologue. Il essaie de comprendre les liens entre ces objets. J'ai travaillé à Berlin, Princeton et Zurich, et mon nom apparaît encore souvent dans les mathématiques d'aujourd'hui. Théorème de Poincaré-Hopf, invariant de Hopf, algèbre de Hopf, fibration de Hopf. Voici mon portrait. J'ai publié la découverte de ma fibration en 1931. Mais comme toujours, il faut dire que je me suis appuyé sur de nombreux prédécesseurs, comme par exemple Clifford, que vous voyez ici, qui a travaillé au XIXe siècle en Angleterre. Commençons par quelques explications au tableau. Blanc, cette fois-ci. Que voyez-vous? Un plan de dimension 2, me direz-vous. Eh bien, oui et non. C'est bien un plan de dimension 2, mais c'est un plan de dimension 2 complexe, c'est-à-dire un espace de dimension 4 réel. Allez, un petit effort. Chaque point dans ce plan est repéré par 2 coordonnées, mais chacune de ces 2 coordonnées est un nombre complexe, qui lui-même est, rappelez-vous, défini par 2 nombres réels. Chacun des axes est une droite complexe, c'est-à-dire que les points sur les axes ont une coordonnée qui est un nombre complexe. Vous voyez par exemple ici le point 2 moins i sur le premier axe. La même chose pour l'autre axe, celui des ordonnées. Ici, on voit le point 1 moins 2i sur cet axe. Notre tableau est magique, mais malheureusement pas au point de nous permettre de voir les 2 plans en même temps. Dans l'espace de dimension 3, il se coupe le long d'une droite, alors que dans l'espace de dimension 4, il ne se coupe qu'à l'origine. Ce sont des axes après tout. Que voyez-vous maintenant? Le cercle? Oui et non. Ce que vous voyez, ou plutôt ce que vous devez imaginer, c'est l'ensemble des points de l'espace de dimension 4 qui sont à distance unité de l'origine. Autrement dit, ce n'est ni plus ni moins que la sphère S3. Bon, bien sûr, il faut un peu d'imagination. Voyons au moins comment cette sphère rencontre le premier axe. La sphère S3 coupe le premier axe sur l'ensemble des points de cet axe qui sont à distance unité de l'origine. Vous voyez, la sphère S3 coupe le premier axe sur un cercle. La même chose est vraie pour le deuxième axe, qui rencontre également la sphère S3 sur un cercle, représenté en bleu. Mais voyons, ce qui est vrai pour la droite horizontale et la droite verticale est aussi vrai pour les autres droites qui passent par l'origine. Ici, vous voyez la droite d'équation Z2 égale moins 2Z1. Mais on pourrait faire la même chose avec toutes les droites Z2 égale AZ1 pour n'importe quel nombre complexe A. Ainsi donc, la sphère unité S3 dans l'espace de dimension 4 est remplie par des cercles. Un pour chaque droite complexe qui passe par l'origine dans notre plan de dimension complexe 2. Attention, sur l'image, on a l'impression que les cercles rouges se coupent, mais ce n'est pas le cas dans la réalité de dimension 4. Les droites ne se coupent qu'à l'origine, et donc leurs intersections avec la sphère unité ne se rencontrent pas du tout en fait. Cette décomposition de la sphère en cercle, c'est moi qui l'ai découverte. Et on l'appelle depuis la fibration de Hopf. Pourquoi fibration? parce qu'il faut un peu y penser comme les fibres d'un tissu. Nous allons observer cela au travers de la projection stéréographique. Imagine donc qu'on projette la sphère S3 à partir de son pôle nord sur l'espace tangent en son pôle sud qui est notre espace de dimension 3. Voici donc la projection d'un de ces cercles qui est obtenu, comme on l'a vu, en prenant l'intersection d'une droite complexe et de la sphère unité S3. Mais il y a beaucoup de tels cercles, un pour chaque droite complexe passant par l'origine. Pour chaque nombre complexe A, nous pouvons considérer la droite Z2 égale AZ1 et le cercle qui lui est associé. Faisons varier ce nombre A, ou ce qui revient au même, faisons tourner cette droite pour observer comment varie le cercle. Remarquez que parfois le cercle semble être une droite, mais c'est tout simplement parce qu'il passe par le pôle nord de notre sphère S3. Observons deux de ces cercles en même temps. En bas à gauche, ce sont deux nombres complexes mobiles, A, rouge et vert. Et vous voyez le cercle rouge associé au point rouge et le cercle vert associé au point vert. Vous voyez que deux cercles quelconques sont enlacés comme les anneaux d'une chaîne. Il est impossible de les séparer sans les casser. Pour le plaisir, nous allons mettre trois cercles ensemble. Regardez la danse de ces trois cercles enlacés. Nous allons prendre plein de droites complexes un peu au hasard et nous allons observer tous ces cercles en même temps, juste pour voir. Les cercles remplissent l'espace et deux d'entre eux ne se rencontrent pas. C'est un exemple d'une structure fibrée. Essayons d'y voir un peu plus clair et revenons au tableau pour un instant. Voyons, nous avons un cercle de Hopf pour chaque droite. Chacune de ces droites a une équation de la forme Z2 égale AZ1, où A est un nombre complexe, la pente de la droite, qui est matérialisée par le point rouge qui se promène sur la droite verte. À vrai dire, l'axe vertical n'a pas une équation de cette forme, mais on peut dire que c'est le cas où A devient infini. Mais n'oublions pas non plus que A est un nombre complexe. La droite verte, elle aussi, est une droite complexe, bien sûr, c'est-à-dire un plan réel. Résumons. Les droites complexes qui nous intéressent sont complètement décrites par un point de cette droite complexe, sans oublier d'y ajouter le point à l'infini. Mais nous avons déjà vu que si on adjoint un point à l'infini à la droite complexe, nous obtenons la sphère S2 usuelle. C'est encore la projection stéréographique. Ainsi donc, les droites complexes qui nous intéressent sont décrites par les points de la sphère jaune, la sphère S2 de dimension 2. Par chaque point de S2, nous avons donc un cercle. Mais un cercle, on peut dire que c'est une sphère de dimension 1, n'est-ce pas? Et tous ces cercles remplissent la sphère S3. Chaque point de S3 appartient à un seul de ces cercles et définit donc un point de S2. Et ainsi, nous obtenons une projection de la sphère S3 sur la sphère S2. Compliqué, n'est-ce pas? Le mathématicien dit qu'au-dessus de chaque point de la base S2, il y a une fibre qui est un cercle S1 et que l'espace total de cette fibration est la sphère S3. Je suis très fier de ma fibration, d'autant plus qu'elle est devenue un objet fondamental en topologie. Reprenons la sphère S2 avec ses parallèles. Au-dessus de chaque point de S2, nous devons imaginer un cercle de Hopf. Observons ce que nous avons au-dessus d'un des parallèles de S2, par exemple l'équateur. Voici ce qui est au-dessus d'un autre parallèle qui se déplace vers le sud. Pourquoi le torse semble-t-il devenir tout fin? Parce qu'au-dessus du pôle sud, il n'y a bien sûr qu'un seul cercle. Au-dessus du pôle Nord, on voit une droite. En fait, un cercle qui passe par l'infini. C'est la droite rouge. Faisons tourner tout ça maintenant. Des rotations. Oui, mais des rotations de l'espace de dimension 4, bien entendu. Pour être honnête, je dois dire qu'une partie de ces figures était déjà connue bien avant moi. On attribue au marquis de Villarceau l'existence de 4 familles de cercles sur le tore, mais on en trouve en fait des indices par exemple dans une sculpture de la cathédrale de Strasbourg. Prenons un tore de révolution. C'est la surface décrite par un cercle qui tourne autour d'un axe situé dans son plan. Observons la section du tore par un plan. Remarquez ici comment j'ai choisi le plan. On dit qu'il est bitangent au tore, tout simplement car il est tangent en exactement 2 points. Mais regardez bien alors, le plan coupe le tore sur 2 cercles parfaits. Ceci est le théorème de Villarceau. Un plan bitangent à un tore le découpe sur 2 cercles. Bien entendu, il n'y a pas qu'un seul plan bitangent. En voici un autre, qui coupe sur 2 autres cercles de Villarceau. Et on peut faire la même chose pour tous les plans bitangents. Il suffit de faire tourner. Vous voyez, par chaque point d'un tore de révolution, on peut faire passer 4 cercles, obtenus en coupant par des plans judicieux. L'un de ces cercles est un parallèle. Un autre est un méridien. Puis un premier cercle de Villarceau. Et un deuxième. Et comme on peut faire la même chose pour n'importe quel point du tore, on voit alors que le tore est recouvert par 4 familles de cercles. 2 cercles d'une même famille ne se rencontrent pas. Un cercle bleu rencontre un cercle rouge en un seul point. Un cercle jaune et un cercle blanc se rencontrent en 2 points. Ce sont des cercles de Villarceau. Regardez bien les cercles jaunes. Ce sont des cercles de Hopf. Vous vous souvenez quand nous observions ce qui est au-dessus d'un des parallèles de S2, on voyait un tore rempli par des cercles enlacés 2 à 2, tout comme ce tore rempli par ces cercles jaunes. Et les cercles blancs, me direz-vous? Eh bien, ce sont les fibres d'une autre fibration de Hopf, celle qui est obtenue en regardant la première dans un miroir. Nous allons prendre un tore de révolution avec ces 4 familles de cercles, l'imaginer dans la sphère S3, puis faire tourner la sphère dans l'espace de dimension 4, et enfin la projeter stéréographiquement dans l'espace de dimension 3. On obtient ainsi des surfaces qui sont également recouvertes par 4 familles de cercles. Ce sont les cyclides de Dupin. Parfois, lorsque le tore passe par le pôle de projection, la surface passe par l'infini. Dans ce mouvement, les 2 faces peuvent même être interverties. L'intérieur du tore est en rose, l'extérieur est en vert. Une simple rotation dans la 4e dimension et hop, le vert devient rose et le rose devient vert. N'est-ce pas magnifique?
music is by my nephew. Okay, especially created for that. So as you can see, we have seen only two chapters, chapter 7 and 8, and the first chapters are more elementary, but you might enjoy seeing them if you wish. Okay.
J'arrête.
Non, j'ai besoin encore, de temps en temps, oui, de temps en temps.
Да, штука вот так, и она сейчас более... Не помнишь?
Oh, oh laisse-le comme ça peut-être, non?
Non, c'est...
Et je vais l'ouvrir après, hein?
D'accord.
Thank you. Okay, first of all, are there questions? I mean, is there something you did not understand, or was it going too fast, or was it obvious, or do you have any comments, any question? So everything is clear? Yes? Great. Okay, so now I want to tell you about the next film I want to produce. So you have seen in this film that the Hopf vibration tells us about the way a line in the complex plane behaves locally in the neighborhood of a point. You see, this is a picture on the blackboard, but we did our best to show you the picture in 4 dimensions. Since this is a complex line, this is a complex line, this is 4-dimensional. This circle is actually a 3-dimensional sphere. And this line here is also a complex line, hence a 2-dimensional object. And what we did in the film was to take this sphere of dimension 3, and in order to see it, we deleted a point from it, and we projected stereographically on a plane, on the space of dimension 3. So we had a look at this picture in R3. And what we have seen is that this line intersected with this sphere, seen in R3, is just a circle. And what we have seen is that if we take two lines, they will intersect the sphere in 2 circles, and these 2 circles are linked. And the Hopf vibration consists simply in just rotating the line around the origin and looking at the decomposition of R3, or better S3, as a disjoint union of circles. And this is what we saw on the film. Okay. Now it's always good to have a feeling for it, either by looking at films or making your own intuition. Like, for example, looking at this picture. This is a real picture, but if you close your eyes, you should see it in dimension 4. For example, this line here intersects this S1 on 2 points. But 2 points is a 0-dimensional sphere. So in the same way as we saw that a 3 sphere is a disjoint union of copies of 1 spheres, in the same way the 1 sphere here is the disjoint union of copies of the 0 sphere. So it's always good to have this kind of game in your head. Sometimes you think in the real category, sometimes you close your eyes and you just think in 4 dimensions. Just an exercise you have to practice, okay? Or you can take a film if you wish, but the film is not good enough. Closing your eyes is much better. Okay, so that's step number 1. What is interesting is not only to understand the local picture of a line in the neighborhood of a point, but what we would like to understand is the local picture of a curve in the neighborhood of a point, especially if the curve is singular. So a typical question that we want to understand is, what is the local picture you now take a curve in the plane, but when I say plane, I draw a real plane because the best I can do, but I think of a complex plane, and now I take a curve like, for example, x squared is equal to y cubed. So it's something like that. Okay, it's something like that. But the real picture, the picture on the blackboard, is a very poor description of the complex picture. The complex picture contains much more information about the local singular point that we have here. And this is what I want to show you. We are going to play the same game. Instead of cutting a line by a little sphere, we will cut the curve by a little sphere. But now you have to keep in your mind that this curve is complex dimension 1 and real dimension 2. So this is actually a real surface. It has real dimension 2. This sphere again is a three-dimensional real sphere. So what you expect is that the intersection of the curve with the sphere will be one-dimensional, just like it was before we had the intersection of the line with the sphere was just a circle. So what you expect here is the intersection to be again a one-dimensional object. So the intersection is a one-dimensional object. So it is a curve in 3 space, and a curve in 3 space is called a knot. So what you are going to see is a knot in 3 sphere. So in this very simple example, x squared is equal to y cubed, you can write all equations easily. Everything can be described with formulas, and you can draw pictures. So what I'm going to show you first is a little film showing this situation for x squared is equal to y cubed. So maybe I show you the film first, and then I come back to the film showing exactly what we see. So here's the
Well, this is done. You might try guessing what knot is going to appear.
Hop. So what you see, too late. What you see is the most simple non-trivial knot. It is called a trefoil knot. I hope it will be obvious why it is trefoil knot in a second, but let me show you this little film and then I explain what it is. Oops. What do you see here? Well, since we draw a picture in complex dimension 2, it's a good idea to draw the axes. Well, we know the axes intersect the sphere and half circles. So one of the two axes is the blue line, and the second axis is the green line, the green circle. So the green circle is x is equal to 0, and the blue line is y is equal to 0. Why is the line a line and the circle a circle? Because I'm taking stereographic projection from a point which turns out to be exactly on the line. Okay, so let me go on. So we are just rotating in 4 space, and you see that the circles, the green circle and the blue circle, rotate again. Okay, now I show you something else. Maybe I should stop now and explain what it is. Could I have some light, maybe?
Свет, пожалуйста.
Oh, sorry. So this is the most important part of the talk. Eh? Do not forget his name, he will be famous soon. Okay, so don't forget, we want to understand the local picture of a curve like x squared is equal to y squared, or x squared is equal to y cubed, in the neighborhood of the origin. So what you see in yellow is the corresponding knot intersection of the 0 locus with the 3 sphere. Now if you want to understand better, there's a simple idea, which is instead of drawing the set of points where x squared is equal to y cubed, you could draw the set of x and y's such that x squared minus y cubed is a positive real number. You see, positive real numbers is a codimension 1 object in complex numbers. It has dimension 1, and complex numbers have dimension 2. So this positive real number is a half-line in complex numbers. So when you look in complex space xy, it is something that has codimension 1 in complex space. So it has dimension 3 in complex space. So it will intersect the 3 sphere in a codimension 1 object in the 3 sphere, in other words, on a surface. And what you see in blue and green is a surface which is the locus of points for which x squared minus y cubed is a real number, positive real number. As you can see, its boundary is the knot, the yellow knot, because the boundary of positive real numbers is just a 0 point. Okay? So what you see here is really a surface. It's called a Seifert surface. It is a surface whose boundary is the given trefoil knot. Now, if you want to understand the situation even better, an idea is, instead of looking at those pairs of points x and y's for which x squared minus y cubed is positive real, you can, instead of taking this half line, you can take other half lines emanating from the origin. So you could look at those pairs of points x and y's such that x squared minus y cubed belongs to omega r plus, where omega is a complex number of modulus 1. So for each omega, which can be any element of the unit circle, you get a half line, and you can look at the points xy for which x squared minus y cubed belongs to this half line, and this produces another surface having the same boundary. And what I'm going to show you now is a picture where omega will rotate around the circle so that the surface will rotate around the knot and describe what we call an open book decomposition. The three sphere will appear like a book having pages, and all pages intersect on the, how do you call that, the binder or the binder or something? I mean the, whatever. Okay, so let me show you the...
What is red?
Blue and green. What's the difference between blue and green?
That's an excellent question, which is beyond the level of today's talk. No, that's okay. Forget it. Okay. Forget it. It's beautiful. Okay, so you see the surface is rotating and is, when omega describes the full circle, the surface will rotate around the knot and describe what we call a fibered knot. The complement of the knot fibers over the circle by this mapping. Now, I will show you several of these surfaces at the same time. Since it's difficult to see everything at the same time, I only show the neighborhood of these surfaces in the neighborhood of the knots. So here you can see 4 of these surfaces rotating around the trefoil knot.
So this is variation over C.
Okay. Let me stop a second. Okay, so this is a foliation of the complement of the knot in the sphere. Okay? You have the 3 sphere, inside the 3 sphere of a knot, and the complement of this knot is foliated by these surfaces. Okay?
All 5 are homeomorphic.
All fibers are homeomorphic. A good exercise is to understand homeomorphic to what? Do you know the answer? They are all homeomorphic to a torus minus a disk. Okay? Okay, now there is some extra structure that I want to show you. And again, don't forget, if you draw this picture in the real plane, what you just see is a stupid cusp. If you take your complex spectacles, you see all this. So it's much better to close your eyes and think about it. Okay. Okay, so here's an extra structure. Notice the following. If x squared, if you replace x by omega cube x and y by omega square y, where omega is a complex number of modulus 1, you can observe that the quantity x squared minus y squared is 1 is preserved, of course, because the modulus of x is equal to the modulus of omega cube x, and the modulus of y squared y is equal to the modulus of y. So if you proceed in this way, you get, and when omega rotates around the circle, you describe in the 3 sphere some closed circles. Okay? One of those circles corresponds to the case where x squared minus y cubed is equal to 0, which is obviously invariant under this transformation. So what I'm telling you is that not only the complement of the knot is filled by surfaces, but also the complement of the knot is filled by curves. This curve is consistent, fixing x and y and rotating omega on the unit circle. And this is what you see here. You see those curves at the same time as those surfaces. So this is the global picture. You see the knot, the surfaces, and the curves. The curves are called the Seifert fibers. So you have the Seifert fibers, the Seifert surfaces, and in the middle you have the trefoil knot. Okay? So that's the way any algebraic geometer understands locally a curve. A curve in the neighborhood of a singular point looks like that. Okay? Let me show you the same film. Well, I did that first, and then we discovered a much better software. You will tell me if it's better or not, I don't know. This is the same, a different texture. Which one do you prefer? This one or the first one? The first one?
Equally good, but this is quicker.
This is quicker. Yeah. I can make it slower. Okay. It is. Okay, now let me show you that what we have seen for a line, what we have seen for this example, turns out to be true in general, for a general curve. So here's this is something that has been known for centuries maybe. Some people say Newton knew it, but so the thing is this. Now I go to the general situation. You have again in C2, and you have a curve that might be very complicated, I don't know, with equation. Let's say P of x and y is equal to 0, where P of 0 and 0 is equal to 0. P is a polynomial. And the goal is to try to understand the situation for a global, in the neighborhood of the origin, by intersecting with a little ball. So the question is, can you describe the intersection of the free sphere with the set where P is equal to 0? And again, this is a knot, or more generally, this is a link. A finite union of knots. And a very old question was to understand what kind of knots we get with this construction. Can we recover the structure of the curve from the knot? Can we recover the knot from the equation of the curve. And this is now very well known. And one of the So one of the main facts is that indeed we had the same property. That is, you can look at the set of points x and y such that P of x and y belongs to R plus. This again is a surface, Seifert surface, whose boundary is the given knot.
And xy lies on the sphere.
Xy lie, let's say, in C2, and you intersect that with the sphere. And this is a surface with boundary whose boundary is the knot, the link. So let me show you some examples. We have seen the example x squared minus y cubed. Let me show you the example. What about this one? X, y, x minus y equal to 0. That's very easy. Xy times x minus y is equal to 0 if x is equal to 0, or if y is equal to 0, or if x is equal to y. So this set here is the union of three lines. So the intersection with the three sphere is the union of three Hopf circles. Easy enough. You have seen in the film this dance of three circles, each one being linked with the other. So you take three of them and you see this. But now the question is, can you draw the picture of this surface for this example? So that would be a surface in free space whose boundary is the union of three Hopf circles. Let me show it to you. Here you see the three Hopf circles. As you know, you can see three circles. One is x is equal to 0, the other one is y is equal to 0, and the third one is x is equal to y. 2 by 2 they are linked like in a chain. And what you see as a surface here is precisely what I have written on the blackboard. It is the Seifert surface consisting of those points x, y, z such that xy, such that x, y, x minus y is a positive real number. It is a surface whose embedded surface in three space, whose boundary is the union of these three circles. So what is the topology of this surface? Can somebody guess it? It is homeomorphic to a pair of pants. But it's a very funny pair of pants, such that the two boundaries are linked. Okay? Okay? Has two boundary components, one here and one here and one here, but any two of the boundary components are linked. Can you guess that? What? What?
So it would not be so easy to fit into this pen.
I don't think so. Okay, now let me give you a theorem. This theorem is due to, I don't know, Puiseux, or I don't know, old theorem. Theorem of Puiseux. So Puiseux is a very famous man, not for being a mathematician, but he's very famous for having climbed the highest peak in the Alps. And many summits have his name as, you look at the map of the Alps, you can see Puiseux there. Right? He's also somehow known in mathematics for this.
Lex 1A inside.
What? Puiseux. No, it's Puiseux. Puiseux. No, it's Puiseux. No A. No. I think so, yeah, Puiseux. Yeah. So the theorem is this. P is equal to 0. Intersection with the 3 sphere is an iterated torus knot. So I should explain what it is. You take a torus and on this torus you draw a curve which is going around the torus p times in one direction and q times in the other direction. You get a complicated knot in 3 space. This is called a torus knot PQ. Then you take a small neighborhood of this knot and you draw a torus around it. And on this torus you draw a P prime Q prime knot. So something rotating around the thing which is rotating as before. And you do that a finite number of times. So you take this torus knot PQ, then you turn around this knot P prime Q prime, and then you turn P double prime Q double prime, etc. You do it a finite number of times and you get a knot. These are called the iterated torus links or knots, and the theorem of Puiseux is that when you look at a locally the structure of an algebraic curve, what you see is precisely this kind of knots. Not only that, but you can discover the integers p, q, p prime, q prime. You can ask your computer to compute them just from the coefficients of p and q. I have in my Macintosh just a simple program. You write the polynomial, and immediately you get the p, q, p prime, q prime, etc., etc. Okay, so that's the kind of final answer describing the local structure of an algebraic curve in the neighborhood of one point. Let me show you.
When you get a link, P and Q are not co-prime.
Yes, when P and Q are not co-prime, you get. Let me show you an example. Look at this one. This one is a torus knot 8-2. You see? So 8 and 2 are not prime together. So you see actually that it consists of 2 knots. One is the yellow one and the other one is the orange one. And what you see in green is the Seifert surface that I described, the set of points for which P is a real positive real number. So this is the case of 8-2, and maybe I can show you something else like 6-3. Anyway, so this theorem of Puiseux is a very good theorem because it tells us what is the local picture that we see for any algebraic curve in the neighborhood of any point. And it's a pleasure because it's a beautiful answer. It's a complete answer, you understand everything. Now I promised, maybe I have some, Victor, how much time do I have?
You have 6 minutes.
Okay, so I have 6 minutes to tell you about a theorem that I have no idea about the proof that I am reading today. I mean, I try to understand. It is a theorem which deals not with algebraic curves, but with something that has been introduced by Gromov called pseudo-holomorphic curves. Pseudo-holomorphic curves. So, since I'm not assuming that you know what the word holomorphic is, I'm not assuming either that you know what pseudo-holomorphic means. So here's the observation. Again, I look in the complex plane C2, and I look at the set of points where Pxy is equal to 0. And look at a point where there is a tangent space. I draw the tangent space as a line because my blackboard is two-dimensional and my curve is one-dimensional. But this tangent line is a complex line. So it's actually a surface, it's dimension 2. And the observation is that this tangent space at some point, at any point, x0, y0, this tangent space is a two-dimensional space, but is one-dimensional from the complex point of view, which means that it is a one-dimensional complex vector space. In other words, if you have a vector v which belongs to this tangent space T, then if you multiply this vector by root of -1, it also belongs to T. So the tangent space to those algebraic curves have this nice property that they are complex vector space. The tangent space is invariant by multiplication by root of -1. Okay, that's an obvious observation. Now the observation of Gromov, which was really, I have no time to explain that, which was really fundamental in the development of symplectic geometry in the last 20 years, is that it is a very good idea to deal with curves which have this property, but maybe not for this standard complex structure. So here's the definition. Definition: an almost complex structure let's say on C2 is a map from C2 to the space of 4x4 matrices, as assigning to any point xy a matrix whose square is minus identity, such that the square is minus identity. So it is something as if it were multiplication by root of minus 1. Multiplication by root of minus 1 has a square minus identity. But you could imagine that there are more general, there are many ways of producing such maps. So this is the definition of an almost complex structure. Then you have the notion of almost complex curves or pseudo-holomorphic curve. Definition: suppose you have such an almost complex structure and some surface. The surface. And a map from S to C2. Then one says that S is pseudo-holomorphic if we have this property. If for every point x0, y0, the tangent space to the surface at the point x0, y0 is invariant by J. So this is the exact same definition by J of this is the exact same definition as the standard definition I had here, except that you replace the standard complex structure here by the almost complex structure here. Now you have no more polynomials, nothing more. You have just this complex, almost complex structure. And the theorem, which is rather recent, published in the Annals of Mathematics, the authors are Micallef and White. Well, the theorem is Puiseux theorem. Micallef and White prove that they extend Puiseux to pseudo-holomorphic curves. In other words, if you take a pseudo-holomorphic curve in this definition for any almost complex structure, even the non-standard one, locally in the neighborhood of a point, what you see is iterated torus knots. And this is a fundamental theorem which is very useful in symplectic topology, and I'm trying to understand it. And I have nothing to say about it, so I think it's a good time to stop. Thank you.